my name is Silvana, and today I will present a bit of my master thesis that is correlated to the Big Cloud project, which was about resource allocation in space division multiplexing networks. So let's start. Medical care, education, entertainment, as well as computational physics, financial transactions, and social network services generate a vast amount of data. So optical networks should offer the capability of transmitting and processing of such big data with low power consumption, low latency, and high level of flexibility at relatively low costs. So to try to handle this problem, many technologies have been proposed for optical networks, but recent studies have shown that the traffic in backbone networks will soon exhaust the expanded transmission capacity, even using WDM or elastic optical networks with single core or single mode fibers. So to handle this problem, the space division multiplexing technology has been studied, proving enormous increase in transmission capacity by introducing the space dimension. So ion SDM technology added one more dimension, but the networks have the problem of spectrum fragmentation that can decrease the spectrum usage efficiency. So this problem happens with dynamic arrival of requests with different teardown times and diverse bandwidth requirements. In this case, these slots are allocated and deallocated dynamically, leading to a state in which there are slots available for allocation, but they are scattered along the spectrum, so they cannot be allocated continuously and contiguously to a light path. This causes inefficient spectrum usage and increases the probability of blocking requests. Moreover, the SDM networks using multiple core fibers have the crosstalk problem, which occurs between adjacent cores and can block slots for allocation, and it also decreases the quality of transmission. So based on these problems, we propose an algorithm, the core and quadrant prioritization RMCSA algorithm, which defines sections of allocation, but to have no restriction on which request can be allocated on each of them. The CQP RMCSA algorithm divides the spectrum into quadrants, each comprising non-adjacent cores and a subset of their slots. We define this order offline. This way, the only online overhead is the search for available slots in the ordered list. So first, the CQP-RMCSA algorithm finds k-candidate paths. After that, the algorithm tries to find a block of available slots in each path using the flood fill algorithm, but since we have a quadrant prioritization, the search is performed only inside a quadrant. The search is only performed on the next quadrant if no block of slots were found in the previous one. So this chart shows the results considering the NSF net topology. Now in the NSF net topology, the PT algorithm starts blocking underloads of 75 lengths, while the CQP-RMCSA algorithm starts blocking underloads of 175 lengths. The CQP-RMCSA algorithm produces the lowest fragmentation values compared to the FCFF algorithm after loads of 50 lengths. So analyzing the results, we conclude that crosstalk has a strong impact on fragmentation. So techniques that do not put an emphasis on crosstalk during allocation were outperformed by the CQP-RMCSA algorithm, employing a rather inexpensive approach in terms of computation. thus proving that our proposed solution to organize the light paths on the spectrum is effective. So this work was accepted and already presented in ICC 2020. So thank you for watching my presentation.